Hello everyone, welcome to today's SF seminar. I'm Sonia. I'm really excited to host today's talk. Today we are very fortunate to have two speakers from Stanford University, uh, Konwoo King and Suhas Kotha, both PhD students working on large-scale language model pre-training. Today they will be presenting their recent work titled Pre-training on the Infinite Compute, which explores how we might rethink pre-training when compute is abundant and data is limited, including new insights on regularization, scaling laws, and examinings. Really glad to have you two both here, and please take it over.
Yeah, thank you. You want to introduce yourself? Yeah, so hey guys, I'm Suhas.
Hi everyone, I'm Konwoo.
Yeah, so today we're going to be talking about pre-training under infinite compute. Yeah, there's a lot of slides. Feel free to ask a lot of questions and please interrupt us in the middle. And please, yeah. Oh, I guess we'll get started then. Cool. So I guess the motivation for this work is that language modeling is working really well these days. And a large part of the success that's driving a lot of language model working is because of pre-training. So training these models that generate that match the distribution of internet web text. And these pre-trained models are really good, especially because they provide wonderful initializations for intelligence and all sorts of downstream tasks. So for example, in 2020, when GPT-3 was pre-trained for a large enough model for long enough, people found that these models were capable of in-context learning. So these pre-trained models provided these really good initializations for intelligence just at the prompt layer. Closer to around 2022, people have really went seriously into instruction tuning and RLHF and alignment and fine-tuning, and found that only sufficiently strong pre-trained models really maximally benefited from RLHF, and these smaller models weren't really benefiting from all these sorts of things. And once the pre-trained model was good enough, instruction following came as a result. Most recently, perhaps around last year, DeepSeek found that when they RL these models, these really strong pre-trained models, they're able to unlock these reasoning capabilities through a lot of RL. But importantly, they found that their pre-trained model had to be strong enough. So when they pre-trained these worse models, they found that the RL didn't lead to this emergent reasoning capability as strongly as if you had taken these larger DeepSeek V3, like their largest version, and RL'd it instead and found much better performance. All of these results kind of suggest that if you can pre-train better models, you can unlock intelligence in all sorts of capacities and really solve all these downstream tasks in a much better manner. However, and maybe what the unpredictable thing is, who knows what's next for pre-training, like if you continue to scale up better pre-trained models. Even though it's really unpredictable what capabilities we get out of pre-training, the actual recipes we follow to continue pre-training better models have actually remained quite predictable over the history of the last 5 years of pre-training. So when you're pre-training a large model, perhaps the primary constraint in practice is that pre-training is really, really expensive. And there's usually some sort of compute constraint that you care about. So people study what is the best possible model you can pre-train subject to various compute constraints. And the study of this has resulted in these very predictable scaling recipes that predict how more compute can be spent to pre-train better models. The first example of this, maybe the most classical example of this, is train compute. So the question is, what is the best possible pre-trained model you can produce subject to a constraint on train compute? Maybe the work on this has settled in kind of this chinchilla scaling recipe, which suggests that for a fixed compute budget, you should not repeat any of your data because you usually have more data than the available amount of compute. And then you want to set the parameter count and token count in a 1-to-20 ratio. And as you increase the amount of compute that you have, you jointly scale up this parameter count and token count. And this is indicated by, on this plot, the different colors indicate different flop budgets. And you show that as you increase the total compute budget, you also increase the size of the models that you train. The other example of people caring about saving compute during pre-training is trying to save inference compute. So even if you minimize the amount of compute spent during training, this might produce a model that's really annoying to inference at test time because you have to keep inferencing this for all the users that want to use your model. The common recipe to handle this is to train these models on much larger token counts than is prescribed by Chinchilla. So even if it costs more train compute, it saves you inference compute in the future. As a canonical example of this, Llama, which pre-trains a bunch of models, pre-trained Llama 8B, which is our most used model out of this. And this model is pre-trained on 15 trillion tokens. And this corresponds to, instead of a 1 to 20 ratio between parameter and token count, this corresponds to a 1 to 2,000. So the models are 100 times smaller than what you would normally do in practice. These are all a couple of different ways in which people have studied how to train the best possible model subject to a compute constraint. And we built up a pretty good landscape of, if you had a finite amount of compute, what is the best possible model you could train if the amount of data you have is really not the bottleneck. However, the problem is that we are actually running out of pre-training data, and that pre-training data is growing very slowly. So Epoch AI has these estimates of how fast the raw text on the internet is growing, and people are finding that the amount of text on the internet is growing at some slow 2 to 4% per year, which indicates that the amount of text is not growing that rapidly. Beyond just text, there are many other domains where the amount of data we have is already really naturally limited. And like, for example, things like rare languages or things like biological domains, we don't actually have that much data over there. And we're already in this regime where we don't have that much data compared to the amount of compute that we have. The core observation that we are going to be operating under this work is that even if the amount of data is growing very slowly, the amount of compute that people are willing to spend on pre-training has been increasing really rapidly, maybe around 4 to 5 times per year. If you take the simple composition of these two facts, you'll notice one very simple observation, that the amount of compute we have per token is really increasing really rapidly. And we can't continue to follow these chinchilla scaling recipes that we've been following thus far. So even if the current practice tells us how to use limited compute when given unlimited data, the actual regime that we care about is how should we use our compute when we're actually constrained by the amount of available data. And we operationalize this under a very simple question that allows us to really study the depths of this problem, which is, how should one approach pre-training when constrained by data and completely unconstrained by compute? Maybe it's worth taking a second here to think about what you guys would do if you were given in this scenario yourselves. So one point to be made is that this regime of where the amount of compute you have exceeds the amount of data is not very different from ML a long time ago before modern pre-training. So for example, classic statistics is really often concerned with the task of like inferring parameters or models from a finite number of samples, kind of ignoring a notion of compute constraint often. And also classical benchmarks like MNIST and PenTreeBank often did implicitly have a lot more available compute than the amount of data that's available for the task. However, I guess there's a pretty different regime that we're living in right now, which is that people are really willing to spend a lot more compute to pre-train better models. And people are going to continue scaling this 4 to 5x compute. And they're willing to do this in a way that they weren't willing to grind out the last 0.1% of MNIST. It is a really important task to continue pre-training better models because it helps so much for so many downstream tasks. In this talk, we revisit this classical question of data efficiency, which has been studied in many times in the past, but really take it to its limit and consider what would you really do if you had infinite compute. And we also get to revisit this with a fresh perspective from the last few years of the success of scaling loss, being able to estimate loss as a smooth function of compute and the amount of data that you have. So we really consider this question of data efficiency from first principles to think about what is the best possible loss that you can achieve. And we really build out the scaling loss to measure this. In terms of a brief summary of our results, we first find that current approaches overfit, and current approaches such as scaling parameter count and scaling epochs and whatever, they really cannot leverage more compute, even if the approaches had more compute available to them. So this overfitting prevents you from leveraging infinite compute, even if you had it, which is kind of an undesirable property. On the other hand, in this talk, we're going to design scaling recipes based on classic algorithms that monotonically decrease the loss as a function of compute. So this gives us both a monotonic decrease, so we can actually leverage more compute if we had it. And the second interesting property is that we're going to achieve this clean power law scaling. And this power law scaling allows us to estimate the performance of our algorithms with different compute budgets. But more interesting, allows us to estimate the best possible performance of our algorithm under infinite compute by taking the asymptote of the scaling law. The asymptote of the scaling law tells you what is the best possible performance if your algorithm truly was given as much compute as it wanted. And we believe that this general tool of asymptotes allows us to make really strong predictions about what algorithms are going to be useful in the future. As a brief overview of our talk, we're going to start off by talking about the baselines that we're going to consider in this work and how current approaches operate. And then we're going to really enter this infinite compute utopia and think about if we really had a lot of compute, what are the best possible recipes that we can do? Here, there's going to be a lot of asymptotes to really estimate the best possible performance and compare different algorithms, showing that algorithms do really matter in this finite data regime. Finally, we're going to take it back and think more about like the practicality of our interventions. Are these things that actually make sense? At what scale do they make sense? Do they continue to matter for like downstream tasks? And we're really going to take it more carefully and see if this makes sense. I think here is a good time to pause. Are there any questions about what we've discussed so far, what we're planning on talking about today?
I guess my question is more on sort of, is this a theoretical exercise or is it like something more practical? Whereas like my understanding is that currently, available token counts are far greater than parameter counts. And so we're not really in an overfitting regime, but maybe.
Yeah, that's a good question. So I think the perspective we're going to take in this talk is that even though right now we are not data constrained, around 5 years from now or something, then we are going to have a lot more compute than data. And then all of these interventions are going to start making sense. So this is going to be a very thoroughly empirical paper in that we're going to be doing a lot of experiments to try to guess at what you would want to do. But the end goal is to make predictions about what you would want to do in a data constrained future, which might not be where we currently are at right now. In terms of the relationship with theory, a lot of our scaling analyses and like algorithms that we try do come from theoretical inspiration because theory does usually consider asymptotics of what happens when compute or data goes to infinity. So this will provide a lot of inspiration for the algorithms, but the actual methodology will be quite empirical. Does this make sense?
Yeah, cool.
Yeah, any other questions at this point? Okay, great. Then we can get into some experiments. Before we do that, let's first get into the empirical setting that we're going to be using in this paper. So to simulate a data constrained future, as mentioned, we don't have enough compute to saturate the 500 trillion tokens of text on the internet. So instead, what we're going to do is we're going to limit our algorithms to a small number of pre-training tokens. In this talk, it'll be 200 million for most of the talk, but I think by the end, in section 7, we're really going to ablate whether these things are, like whether they generalize or not. In terms of the actual pre-training recipe used, we use an optimized pre-training recipe. So this is things like using transformer, using an Atom W optimizer. And this pre-training recipe is borrowed from RIN, which is this wonderful pre-training framework that we and a couple of others at Stanford have used to pre-train a model that's stronger than Llama 8B. So we know that we're like faithfully representing practice in terms of what works for language model pre-training. Since we are assuming infinite compute, we think that the standard regime of chinchilla scaling and this inference compute overtraining is kind of not what we're interested in. We're really like, if we know that training larger models is going to help us, we're going to train these larger models to get more data efficiency. So in this setting, we're going to be training models that are much larger than what people currently train. So 30 times larger than chinchilla, 3,000 times larger than standard overtraining practice. But hopefully it reflects that in a data constrained future, we are also willing to train much larger models. In terms of the metric that we use, we are going to be sticking, for most of this talk, we're going to be using validation loss. We find that validation loss, many people have found previously that validation loss is a great proxy for the capabilities of a model, especially in downstream tasks and for controlled algorithm changes. We also confirm ourselves later in this talk that this actually does lead to downstream accuracy benefits. So we're going to stick with validation loss for now. And finally, we're not going to allow for any human supervision. It's a common practice these days to basically incorporate a lot of external supervision to train better models, such as prompting models to generate synthetic data, using external reward functions or external data or distillation. These are things that we're not going to allow ourselves to do because we are mostly interested in this pure question of what is the most value we can extract from the data, even though these are things that might help. Hopefully, these are things that stack on top of what maximum value we can extract from the data in the first place. Yeah, please ask any questions about the setting. Okay, if not, then we can start jumping into experiments. So the first thing that we're going to do is we're going to characterize maybe people's gut reaction to how well do existing methods handle data constraints. So I think there's two main ways in which language modeling people, at least in the open, have really considered this in the last few years. One is that if you have a lot more compute that you're willing to spend and you have a limited amount of data, one thing you can do is you can repeat the data. This is like a pretty classical, like epoching the data is a pretty classical thing that people have been doing for a long time. But there's been recent work, like in the last 2 years ago, there's been work showing how it helps pre-training. There's also another reaction, which is that if you're bottlenecked by the amount of data, you can continue to train larger and larger models because larger models happen to have a better inductive bias and learn better from a finite amount of data. So we're going to characterize the performance of both of these recipes in our data constrained regime. The first thing that we try is epoching the data. In this plot, we're training our 300 million parameter models on 200 million tokens. And on the x-axis, we vary the total epoch count of training. Each of these points is a separate pre-training run. What we notice is that as we epoch the data, we actually get a performance improvement. And it looks like 8 epochs is better than epoching the data once. But it does not go forever. And if you continue to try to epoch the data more and more, your loss starts going up. At each of these points, for each epoch count, we also tune the learning rate just to make sure we're getting the maximum value out of these pre-training runs. So epoching, as perhaps expected, eventually overfits, and it's not some operation that you can do forever. The next recipe that we try is we try increasing the parameter count. So now, at each x value, we are trying a different parameter count. And for each parameter count, we are jointly tuning the learning rate and the epoch count in an attempt to get the best possible loss for this fixed parameter count. So we try this for 150M, 300M, 600M, 1.4B. What we find is there's very strong diminishing returns to increasing the model size. And even at the end of the spectrum, we're actually observing this overfitting in which the larger models are actually, this largest model is actually performing worse than the 600M model. So one conclusion that one might draw from this, that one may incorrectly draw from this, is that this point over here, this 600 million parameter model trained for 200 million tokens, is the best possible performance under infinite compute. Now, if you are following these recipes, this may as well be the best possible loss that you can get. Interestingly, in this infinite compute regime, the actual algorithm that you use to train on the data matters a lot more. And this is kind of what we're going to cover for the rest of this talk. The next recipe that we're going to consider is the natural reaction of that if we are training all of these over-parameterized and epoch models, perhaps it's necessary to regularize the pre-training to get the maximum value out of this data, especially since these models are so much larger and epoch so many more times than standard practice. The first thing that we do is for each parameter count, we jointly tune the learning rate, epoch count, and weight decay. We aim to be thorough about this. So what we do is for any hyperparameters that we display, that we find locally optimal hyperparameters. What that means is that these hyperparameters of 3, -3, 16, and 0.8 for the 150 million parameter model, if you incremented or decremented the learning rate, incremented or decremented the epoch count, or the same for the weight decay, all of those 6 neighbors perform worse than this choice of hyperparameters. So this indicates that this is really like our best attempt at the best possible loss for this parameter count. When we tune these hyperparameters, we made a pretty finding that kind of went against our knowledge, which is that the largest models, the over-parameterized models especially, benefited from a weight decay that's much, much larger than standard practice. So usually when people pre-train language models, they'll use a weight decay of 0.1, most likely cargo cultured from the original GPT-3 paper. But what we find is that when we're tuning these models, especially for these over-parameterized models, the optimal weight decay is over 30 times higher than the standard practice. And it's really important to use weight decays that are like 3.2, which is much higher than what people normally do. After we tune these hyperparameters, we find a pretty large loss improvement over the standard recipe. So this red recipe over here is the standard parameter scaling epoch recipe that we had seen in the previous section. Now what we're going to do is, in addition to tuning the learning rate and epoch count, instead of fixing the weight decay to be 0.1, we're also going to tune the weight decay in tandem with these and find that it makes a huge gap, especially for our largest models. Though this is the first exciting thing that we're getting this much higher performance, the second nice thing that we find is that the loss actually follows a clean power law. So we find that for our 4 points, we're able to fit this power law that kind of reasonably interpolates the data. So This power law has a couple of interesting properties when we fit it. The first interesting property about this power law is that if you look at the model scaling exponent, or how fast the loss drops as a function of the parameter count, we find that the exponent is close to 1. This is pretty different than the data unconstrained regime, which is studied by chinchilla scaling, where people in practice usually find exponents that are much, much smaller than 1. So for example, the chinchilla model scaling exponent is 0.34. This indicates that in the data constrained regime, you're getting a much faster improvement from increasing the model size. Perhaps what's most interesting about this is that we actually don't care about this exponent. In this truly infinite compute regime, though this exponent is nice to saturate the performance, what we actually care about is the limit as the parameter count goes to infinity, because we're willing to train as large models as possible. So what we find is that the actual loss that we find, the actual asymptote of this power law, 3.43, is something that captures our best estimate of the best possible loss under infinite compute. I see some questions in the chat, so perhaps I'll answer them. Oh yes, so for the data set for this paper, we are using DCLM as the pre-training corpus. Thanks for clarifying. For all these initial set of experiments, we're going to be using 200 million tokens. And in a later section of this talk, we're going to be seeing how these performance gains change as you change the amount of data seed tokens given. How do you trade off between larger model with higher regularization versus just smaller model, or MOE where active parameter counts are less? So over here, what we are finding is that if you correctly tune the regularization, which again is not something that actually costs you compute, it's always better to train these larger models. So it's more a function of how big are you willing to train a model that determines how big of a model you want to train. This regularization you should tune per parameter count, and you'll always get an improvement from doing that. In terms of the relationship with MOE, yeah, I think the MOE has like a pretty interesting relationship in terms of like the parameter count and inference time. I think for now, we're really not going to think too much about the parameter count and inference time, and perhaps we'll revisit this as a later point about like how many, like which methods make sense if you care about inference parameter count rather than train parameter count. For now, think of the parameter count as just a proxy for how much compute we're spending, and we're using this to build the clean scaling laws. Any other questions? If not, I think the main takeaway is that we're really excited by the tool of asymptotes. If you correctly tune these hyperparameters and correctly think about how to train these models, we find these nice monotonic relationships, which actually allow us to very cleanly predict how loss is going to change as a function of compute. And this really allows us to estimate the best possible loss under infinite compute, which is the regime we're going to operate in until we care about like the practicalities of these methods. Cool. For this next part, what we're going to discuss is we're going to discuss an alternative scaling recipe that spends compute in a different way than parameter scaling does. So even though parameter scaling is one way to spend compute, it's not the only possible way to spend more and more compute to train better models. A technique that worked really well in classical literature is ensembling. So instead of training a 5x bigger model, what we're going to do is we're going to train 5 models of the same size. So not increasing the model size yet, which is training multiple copies. And each of these models is going to be given a different data order and a different initialization, but is otherwise the exact same training procedure. After we train these models, we're going to take them and we're going to average their logits at inference time. So this is the simplest way to aggregate these models after we've trained them completely separately from each other. So this is one way in which we can spend more compute. A finding that we found really, really surprising is that instead of training these bigger models, instead of training these around 5x bigger models, we find that it's actually better to train multiple copies of the same model, even when matching the total parameter count. So in this plot, the purple curve over here corresponds to something you're familiar with. It's the parameter scaling as you tune regularization correctly, which follow the power law. In addition, what we do is we take these 300 million parameter models, we follow the exact same training recipe and just train multiple copies of them. Each of these points corresponds to a 1 ensemble, 2 ensemble, 3 ensemble of all like 400 million parameter models. And we're matching the total parameter count of the ensembles, since this kind of corresponds to how much they cost at inference time. Under these scaling laws, we find a pretty surprising finding that instead of training larger models, which is maybe perhaps a de facto paradigm in language modeling, it's actually better to train multiple copies of these models and aggregate them after the fact. What's extra nice is that increasing the ensemble member count follows a really clean scaling law. So what this corresponds to is that if you increase the total number of ensemble members, this also decays at a rate of exponent 1. And this has an even lower asymptote of 3.34. There's a question about, did you track gradient norms during pre-training, and how did the gradient explosion near the end phenomenon behave with your chosen weight decay? Do you know if it got better or worse? Great question. We didn't track the gradient norms, so we have them, and you're free to look at our weights and bias logs. We've open sourced all of this, so feel free to look at it. I don't remember the gradient norms. In terms of the gradient explosion, I guess we've seen this phenomenon with this high weight decay pre-training, which I guess is corroborated by prior work, which is that when you train with high weight decay, your loss improvement is slower at the start of training and then becomes very rapid at the end of training, which I think is perhaps related to the gradient norm explosion. We didn't track too much about the fine-grained details about what happened, but we did find that it was better terminal loss to have high weight decay, so we stuck with it. Yeah, good question. So cool. What's really encouraging about this is now ensembling is a recipe that also has clean scaling, but it has a lower asymptote. And this lower asymptote kicks in at like pretty low parameter count, or not like relatively like reasonable parameter count, such that we can actually observe the crossover, which kind of tells us that we're going to be fine. Yes, so there's a question about what the ensemble structure is. We're using the most vanilla form of ensembling, which means that we have multiple copies of the model, all trained completely independent of each other. And then after the fact at inference time, we're going to average their like logits. So there's no MOE structure to it. Maybe perhaps an experiment of interest is that we had tried training these models jointly. So right now we're ensembling. One really important component is that we trained each model independent of each other. If we try training these models jointly together, so constructing a structure which is 5 models held together that where their logits are averaged at training time, not only at inference time, we find that this type of model barely offers any improvement over a single model, suggesting that the reason that ensembling is helping is not about sparsity, but it's more about the random training trajectories that are happening. So to give some additional intuition for why we think ensembling is helping, it's obviously hard to tell the exact explanation for why ensembling is helping, but perhaps our core intuition comes from this prior theory paper from this wonderful theory paper by Zeyuan and Yuanji. And what they suggest is that data often has this multi-view property, which suggests that training examples, there are many possible features that correctly classify a variety of training examples. To best fit all of the training examples and generalize to the test set, it's best to use all of these features. However, single models, no matter how large, have this bias towards learning only one of the possible features, only a couple of these features that correctly classifies the majority of the data set and then leverage memorization to remember like the rest of the data set. Under this view, ensembling is quite nice because the randomness that you get from independent training trajectories is allowing you to learn the whole set of features, even though each individual training trajectory is not going to learn all of the features. And this is why we suspect that just making the models more sparse isn't what's going to solve this. What you really do need the independence property to get the major benefits of learning all of the different features. One experiment that we conduct in this direction is that for each ensemble member, earlier, we have seen this black line, which shows the loss as a function of the number of ensemble members that we have. So this was the scaling law that we saw earlier, but it was also each ensemble member was trained with the exact same hyperparameters as the best hyperparameters for a single model, or k equals 1. What we actually care about is the asymptote as the number of ensemble members goes to infinity. So what we study is whether the optimal hyperparameters remain the same as you send ensemble count to infinity. So for 12 different epoch and weight decay pairs, we try fitting these scaling laws by training 5 ensembles. What you find when you take these limits is that under the limit of infinite compute, first of all, at finite values of k, the actual ranking between the hyperparameters changes, and under the limit of infinite compute, the best hyperparameters for an ensemble correspond to each member being trained with less weight decay and more epochs. Intuitively, this is suggesting that you want each model to overfit to the training data in its own unique way to learn its features maximally, and you don't care about the memorization as much because you're going to be able to ensemble over a diverse collection of models that you get from the randomness of initialization. and data order. So this allows you to actually, you find that it's actually best to pre-train these ensembles by using more, well, like hyperparameters that encourage more overfitting than standard pre-training. So this concludes our ensembling recipe, which kind of gives you a better way to pre-train under this infinite compute limit. I think at this point, I'm going to hand it over to Konwoo.
Hello. Okay, so Suhas has kind of introduced like the main scaling recipes we use in this paper, which to recap, we have sort of the current standard recipes people use. Then we have our regularized recipe where we really crank up weight decay. And then we have sort of vanilla ensembling where for a fixed parameter like count for the individual members, we can ensemble multiple numbers together. And so in this section, we're going to look at how far can we push our performance if we sort of compose all of these like data efficient interventions that we've introduced so far, and how much better is this compared to the current practice. And so sort of the main interventions that we've introduced allow us to sort of scale compute along multiple axes now. So we have scaling along sort of the parameter axis, but now we also have scaling along the ensemble like member axis. And so what we can now do is we can sort of compose these two scaling axes to characterize the best possible performance like under infinite compute under this double limit as we send both of these quantities to infinity. So concretely, what this limit looks like is it's a limit over two parameters, which are n and k. And n here corresponds to the number of parameters in each ensemble member, while k corresponds to the number of ensemble members that we have. And h is sort of a shorthand to denote like sort of the minimum over like all of the hyperparameters we're considering, which in this case is like learning rate, weight decay, and epoch count. And so if we compute this if we can estimate this double limit, this sort of characterizes the best possible performance of what we're going to call a joint scaling recipe as we send sort of both of these quantities to infinity. And so concretely, we sort of introduce a way to like estimate what this limit should be equal to. And the way in which we're going to do this is we're going to first take the inner limit. And so taking the inner limit here corresponds to sending the number of ensemble members to infinity for a fixed ensemble member parameter count and a fixed data set size, where we're selecting our hyperparameters to give us the ensemble with the best possible asymptote. And so we sort of introduce like a heuristic to estimate hyperparameters that give you this best possible asymptotic performance. And so if you look on the plot on the left, what this is showing you is at this 200 million data size that we're considering, the x-axis here is the number of ensemble members, the y-axis here is our validation loss, and the different colors correspond to ensembles with different member parameter sizes. So the dark blue color corresponds to ensembles with 150 million parameter members, then 300, 600 million, and then 1.4 billion parameters. And for a fixed member parameter size, we can scale the number of ensemble members and we can fit a power law to these losses. And so you can see that sort of even as you increase this member parameter count, the power law fit is pretty clean. The exponents all look pretty similar, but you get an increasingly better asymptote. And so once we sort of have an estimate for this inner limit for different values of n, what we can now do is we can back out sort of the asymptotes of each of these individual power laws. So for this first power law for the 150 million parameter ensembles, we can estimate its asymptote. And then we can do this for each of the other parameter size ensembles, and this will give us 4 individual asymptotes, which are the points on the right. And once we have these 4 individual asymptotes, we can fit a second power law, which corresponds to sort of the second limit and the original double limit we introduced in the previous slide. And the asymptote of the second power law sort of characterizes the best possible performance of the joint scaling recipe. So there's a question which says, this graphic is already with the optimal number of epochs or single epoch. So yeah, each point here is sort of trained with like the optimal number of epochs to give you like sort of the best possible ensemble. So it's like not a single pass setting. And for sort of the specifics of like what this like heuristic hyperparameter recipe looks like and the exact values, you can see like the appendix of the paper where we kind of like detail all of this and do like various ablations. So sort of to summarize, like when you do this two-stage procedure to estimate this double limit, you get this estimate of like the best possible like performance of the joint scaling recipe. And so that's going to correspond to the asymptote of the second power law, which in this case is 3.17. And so if you look at the sort of the right plot here, you can see that the red dotted line corresponds to the best possible performance of our standard recipe. We've already observed that we can do much better by increasing regularization, which is the dotted purple line. But by doing this optimal joint scaling recipe, we can show that you can, like in the limit of infinite compute, you can get even much better loss. And so to sort of summarize what this looks like, the first approach we had was sort of like the fact that current approaches overfit, and that's like the best possible red dotted line. And then we introduced regularization, which has clean power law scaling and lets us now start to look at the asymptotes. Then we introduced ensembling, sort of vanilla ensembling, and ensembling has both a lower asymptote than regularization, and at a certain point gives you sort of better point-wise loss as well for a fixed parameter count. And finally, now with sort of the composition of all of our recipes, this joint scaling recipe, we can get an even lower asymptote, so around like 3.17, which is like much, much better than sort of what we're starting with, which is a red dotted line. And so this is sort of the summary of like the core set of experiments at like 200 million tokens, which sort of shows the iterative data efficiency gains you can get by like introducing these interventions one at a time and finally like composing them all together. And so sort of the remaining sections are going to be a lot of like rigor checks on these findings. So rigor checks as you scale your data size or like how this corresponds to downstream accuracy and things like that. So I'll take a moment to pause here and like answer any questions about this figure.
We have several questions in the chat.
Okay, so there's this question that says, does this say the larger N and K are, the better the performance is? Yeah, so essentially like in this data efficient regime, if you properly introduce regularization, like both as you increase N, so as you increase the parameter size, and as you increase K, you can get smooth gains in performance. And we believe this is like a pretty desirable property of like the optimal learning algorithm. Like the optimal learning algorithm should be able to leverage the additional compute you have on hand to give you a truly better model. It probably shouldn't be something that just like starts to overfit. And so we believe that like in chasing these types of recipes with smooth scaling, as you increase compute, you can find like truly better sort of pre-training objectives. Okay, let's move on then. And so sort of as we've discussed, all of this is at like the 200 million token scale. And so we're now going to look at like what happens as we increase the seed token count. So as we move beyond 200 million tokens. And roughly what this section is going to look like is essentially we're just going to repeat every single one of our experiments at like each one of like a larger seed token count. And this will show us like both the sort of the raw performance, and it'll allow us to contextualize the loss improvements that we've seen at 200 million token counts relative to if we had truly had like a larger amount of data. And so essentially like we're going to sort of introduce this by like repeating all of our experiments, and then we're going to start building sort of the data scaling law. So like how our asymptotes change as we have more and more pre-training data. And so to start for sort of the standard recipe sort of corresponding to the baselines that we have right now, what we can do is for each seed token count, which corresponds to this x-axis, so for 200 million tokens, 400, 800, and then 1.6 billion pre-training tokens, also all like from DCLM, we can find sort of the best possible loss of like our standard recipe. And the best possible loss here corresponds to just like doing this pretty comprehensive like grid search over like all of our hyperparameters in the way that Suhas described at each of these seed token counts until we start to observe this like overfitting. And once you like sort of train these models at each of these seed token counts, you can fit this sort of preliminary data scaling law for like the standard recipe, which characterizes like if you had more and more data, like what's the best possible loss you would get. Similarly, we can do this for the regularized recipe, so the one where we just introduced like a very large amount of weight decay. And concretely, what this is going to look like is for each seed token count, we're going to estimate the asymptote of the regularized recipe. So on the left plot here, you can see that the different shapes correspond to different seed token counts. So the circles correspond to 200 million, triangles 400, squares 800, and crosses 1.7 billion tokens. And so just if we look at the circles, we can again fit the power law for the regularized recipe, and then we can estimate its asymptote, which characterizes like the infinite compute performance of the regularized recipe at 200 million tokens. Then we can do this, again, the same procedure at just the higher token count for 400 million tokens, which gives this triangle. And then we can do it again for 800 million tokens and again for 1.7 billion tokens. And so each one of these points here corresponds to sort of this double limit by first taking a limit over parameter count and then starting to build this data scaling law as your data set size goes to infinity. And so the purple dotted line here corresponds to the data scaling law for this like regularized scaling recipe. And so we're also going to do this for the ensembling. So if the regularized recipe was 2 limits, the ensembling data scaling law is going to require 3 limits because we have to take a limit over ensemble member parameter size, ensemble member count, and then data. And so essentially, I'll sort of skim over this, but the idea is like, we're just going to repeat this procedure 3 times now. So first, what we're going to do is the color here corresponds to the ensemble member size. The shapes correspond to the data set size. And so we're going to take this limit as ensemble member count goes to infinity. These are all going to be asymptotes as member count goes to infinity. So we're going to do this for each one of our like model sizes at each one of our data scales. And so this is going to give us a set of 16 total asymptotes. And then what we're going to do is we're going to fit another limit through all 16 of these asymptotes. And so if you fit a limit through the first 4 set of asymptotes, it's going to correspond to this gold circled point, which sort of corresponds to the infinite compute performance at 200 million tokens, which we've already seen is like 3.17. And we're going to do this for each of the other 3 token counts. And once we do this for all of the token counts, this gives us 4 asymptotes, which characterize the data scaling of like the ensemble asymptotes. And so this sort of I see there's a question. Okay, so the question says, you evaluate recipes by the asymptote of a scaling law as n or k goes to infinity, not by a fixed compute point. How often do rankings by asymptote invert the ranking at realistic budgets, say 10 to 100x chinchilla compute? Any evidence of non-monotone crossovers before the asymptote? I imagine that if crossovers are common, the asymptote could be a proxy for near-term decisions. Yeah, so this is a really good question. So I guess there are several like related answers to this question. So maybe like first, just if we considering this crossover question in the context of like ensembling and ensembling hyperparameters, Suhas briefly showed this slide before about how the optimal hyperparameters for an ensemble like change as you increase the ensemble member count. And so essentially like the optimal performance, like if you had like 4 ensemble members for like a fixed hyperparameter configuration, would look different if you compared the performance at like 8 ensemble members or even like the asymptote. And so essentially like what we're doing is like we're sort of optimizing for the asymptote, and if you optimize for the asymptote, you're sort of guaranteed by definition that there's going to be some compute budget at which you sort of dominate like the baseline you're comparing against. And in sort of the next section of the talk, we're going to show that like this compute sort of crossover, or sorry, like dominance points exist. And we can push this compute like dominance point to the left by doing tricks with like distillation. And I guess by like compute dominance here, I mean like for some like fixed like inference compute threshold. So like if you were only willing to inference, say like a 300 million parameter model, like can ensembling still help you even if like the asymptote is only better at like an infinitely large model parameter size. And so we'll show like you can do sort of additional like algorithmic interventions to sort of push this point further to the left so that if you have a small inference compute budget, you can still benefit from the asymptotic gains of ensembling. So hopefully that touches on sort of some of the questions you had. Why is the limiting loss 1.89 of the standard recipe better than the other 2 recipes? Yeah, so it's a good question. I think that you should take these data scaling laws with sort of a big grain of salt. Like there's a lot of noise in sort of the measurement of them. Maybe sort of if we look at the far right figure, there are a couple like main takeaways we kind of want you guys to have. And so sort of one thing is that um, the asymptotes and like the exponents of all three of these laws are like pretty similar. So like all of the exponents are like sort of around 0.23 or 0.24, and all the asymptotes are close to like 1.9-ish. And so there's like a large amount of noise still, but like this kind of suggests that because these two quantities are very similar, like the data efficiency wins that our like ensembling and regularized recipes are giving you are, this is a very preliminary suggestion that these wins persist across like higher token scales, like given that these like exponents and asymptotes are similar. The second thing is that like if you look at sort of the gold line versus the red line, this plot sort of characterizes like the true like data efficiency win of a recipe at infinite compute. So if you wanted to match like the infinite compute performance of the joint scaling recipe, which is like 3.17, you would need approximately like 5x more data if we project it onto the red line, which is like 1 billion tokens. And so that's where we're getting these like 5x data efficiency numbers. We're taking the loss of like our best possible like a data efficient recipe and projecting it onto the data scaling law of the standard recipe. And so I guess it's also worth saying that like even if you don't like fully trust these asymptotes that we're throwing at you and these like double and triple limits that we're throwing at you, like the realized losses of our biggest models, so like the loss of our biggest like 5 ensemble of 1.4 billion parameters still gives a very large data efficiency improvement if we project it onto the red line. So that ensemble gives you something like a 3.7x data efficiency win. So even if you like don't trust the asymptotes of sort of the regularized or ensemble recipes, like we can give you concrete models and like the actual training recipes for those models with realized losses that are like truly more data efficient than like the standard recipes as well. And so yeah, maybe to summarize, like there is a lot of noise in sort of these scaling law constructions and these asymptotes, especially the data scaling law ones, because you're sort of taking like many limits to chain it together over not that many training runs. But I think we have like sort of preliminary evidence that like some of these gains are at least like pretty real, and even like in the non-asymptotic sense, like in a realized model sense. Yeah, and so that sort of concludes like the data scaling section. So like sort of preliminarily, it seems like our data efficiency wins should persist. And so now we're going to look at what we can do with distillation. And so sort of as like some previous questions have alluded to, like a lot of these data efficiency wins we're observing are right now in the asymptotic sense. But like how truly useful is this for a practitioner? Like we don't have like infinitely large models that we're inferencing for like OpenAI or whatever. And so we're going to look at like what you can do with distillation and whether you really need these large parameter counts both at inference time and then later at training time. And we're going to give sort of a positive answer, surprisingly, to both of these questions, that you can train more data efficient models, even if you don't have a large model at inference or a large model at training. So this will kind of suggest that like data efficiency is not purely a function of model capacity. It's more a function of like a better learning algorithm. And so we're first going to talk about like, let's say we don't want to inference a large model, like what can you do? So concretely, we're going to look at a really, really simple distillation algorithm. And essentially, we're going to look at like a variation of the simplest possible algorithm, which is sequence level knowledge distillation from like many years ago. And we're going to do this in a slightly different way by mixing in real data. So there will be 3 steps. First, we're going to train some teacher model using one of our data efficient recipes on D tokens. Then what we're going to do is we're going to take this teacher model M prime and we're going to sample from it unconditionally. So we're not going to have a prompt. A lot of like sort of data efficient pre-training papers use some kind of prompt that says something like rephrase the data to be like equivalent, make it like a Wikipedia article or make it like QA form. We're going to do this completely unconditionally and generate a data set of D prime tokens. And then we're going to train our student model on from scratch on the mixture of these 2 data sets. Okay, so there's another question on weight decay, but I'll delay this maybe closer to the end of the talk. Okay, so yeah, to sort of summarize, like this distillation algorithm has like 3 steps. Like first, train your teacher model however you want, then sample from it unconditionally, which will like sort of approximate the teacher model's distribution, and then train a student model from scratch on a mixture of these 2 data sets. And importantly, like this has no human prior because of like the unconditional sampling. And so we're going to look at like, what does this distillation algorithm give you? So to start, we're going to look at ensemble distillation. So what the setting is saying is we're going to have 200 million tokens again. And we're going to look at what is the best possible 300 million student you can train. So the purple line on this plot corresponds to the standard regularized scaling model that we've seen, which has like a smooth power law scaling and an asymptote of like 3.43. The light blue line corresponds to the ensemble scaling of 300 million models. So each ensemble member has 300 million parameters, and we're increasing the ensemble member count. So 600 million, 900, 1.2b, etc. And this also has smooth scaling as we've seen. And then this pink star corresponds to if we were to distill an 8 ensemble, which has 2.4 total billion total parameters, into sort of the small 300 million parameter model. And this distillation procedure is sort of the algorithm we've outlined. And you can see that like essentially, if you do this distillation procedure, you can train like a really, really data efficient 300 million parameter model. This model is not only much better than the asymptote of the regularized recipe. Keep in mind the asymptote of the regularized recipe is like an infinitely large model. It's also better than sort of this optimal like 4 ensemble, which has like 1.2 billion parameter total parameters. And so concretely, like this distillation procedure sort of preserves around like 83% of like the loss improvement that ensembling is giving you over like normal like the baselines we're considering. And so it sort of shows that like if you do distillation properly, importantly, we find this like mixing procedure to be super, super important. And we have like a lot of details on that in the appendix. You can preserve data efficiency and you can push back the sort of inference compute versus loss frontier to the left using ensemble distillation. So if you have some data efficient recipe and you properly distill it, the Pareto frontier of data efficiency can be significantly improved, which is like a really nice thing to know as like a practitioner. So ensemble distillation is nice, but maybe now we can also think about like, okay, we got rid of ensembles at test time. Can we also just get rid of them at train time? And this at first glance would seem like very unlikely given that there's no reason to assume that like students can outperform their teachers. And there have been like a lot of sort of recent papers in the past year or two claiming that like training on your own generation will like result in model collapse and like how like synthetic data can be like bad for the final model. And so I think there's a lot of reason to doubt that this is actually possible. But we very surprisingly find that you can like improve your performance and you can improve your performance by like a lot. And so again, this is the same plot, but now with one extra line, which is the self-distillation line, which is the green arrow to the green star. And so what this is showing is you take this 300 million dense model, and we're going to repeat our distillation procedure into another 300 million model with the exact same architecture and the same parameter count. The only difference is like this guy is initialized from scratch and trained on the mixture of this guy's unconditional generations and like the true pre-training data. And what you see is that like self-distillation gives you like a huge improvement over the teacher. Like this green star is in fact essentially matching the asymptote of regularized training. And it's matching the asymptote like at 300 million parameters without using ensembles at all, only using 300 million parameter models. So we got rid of big models at training time and big models at test time. And we're still getting something super, super data efficient, which is like very surprising. And so to maybe like give you a little intuition for why self-distillation actually helps, sort of the same paper from before about like the intuition of why ensembling helps suggests that self-distillation can be seen as this implicit ensemble between like the first teacher model you trained and this like fresh student model that you're like doing the distillation into, which suggests this really interesting connection between like distillation, sort of this like prior free synthetic data that we're making a case for, and ensembling. And this is something like it's a general direction that I think we're both very excited about. Like in general, like looking for types of synthetic data that don't require you to bake in any kind of like human prior equivalence. And like I guess we view self-distillation as a very preliminary example of this. Okay, there's another question in the chat. The question is ensembling. Somewhere in the paper, we suggest that data order variance yields most of the ensemble gain. Have you measured pairwise correlation of token level losses across members? And is ensembling efficacy predictable from the correlations? This would be cool because it might let us manufacture the right diversity cheaply. Yeah, that's like a really good question. I think like maybe it's worth saying like we did sort of the bare bones like minimal implementation of ensembling, like almost like the simplest possible instantiation that you can think of. So we didn't really look at these types of like pairwise correlations you're suggesting, and I think like there's a large amount of room to sort of push ensembling further. Like right now we're only ensembling over the randomness in data order and model initialization, but you can kind of ensemble over like whatever you want. So for example, you could ensemble over models like trained with different optimizers or like trained in like different ways and like with other additional sources of randomness. And like I think there's like a ton of room to like sort of further push like the data efficient like frontier like with different kinds of ensembling. And this is really just like the raw like proof of concept of like what the baseline can get you. And so like in short, I don't think we really have a clear sense of like this right measure of diversity necessarily, like what that would actually look like. But initially it seems like data order is like a pretty good proxy to like give you good performance. Okay, so yeah, to kind of summarize, like distillation is really good. You can get rid of ensembles at inference time, and you can also get rid of them at train time and still get really data efficient models, which is great. So now we're gonna look at like downstream benefits, which is like we've only looked at validation loss up to until this point. Does that actually correspond to truly better models? The short answer is like we find that it does. And so we sort of look at like downstream benchmark performance of these small models on sort of 3 different pre-training benchmarks that people use for evaluating small models. And like the left plot here is sort of the set of all of like the models we've trained in these experiments so far at 200 million tokens and like the validation loss curves. And the right plot here is every single one of these models like evaluated on these downstream benchmarks. And qualitatively, what you should see is like the scaling is noisier, but like all of the trends roughly like seem the same. Like you get better downstream models as you scale both like parameter size and ensemble member count. Like sort of the standard recipes that people use right now sort of still suffer from like this overfitting issue. And even like the distilled models still exhibit really strong performance like at their parameter count. It's also worth saying that like we totally ignored downstream benchmarks until like the very end of this project because we were big believers in val loss. And so it was actually a pretty good sort of benchmark for like true generalization, and that like we didn't look at these numbers at all until our advisors were like, you should like add this as an experiment. And we were like, okay. And so I think we are pretty confident that even with just chasing validation loss in this pretty narrow sense, like you can get like better generally pre-trained models, which is nice. Okay, another sort of rigor check we're gonna show you now is like all of these experiments are on pre-training these models from scratch. What other settings can you use this on? And so maybe the natural extension is sort of this like continual pre-training setting where I already give you a pretty good pre-trained model, and maybe I give you some rare data in some domain I want you to like do a really good job on. Do these data efficient recipes also transfer to this type of setting? And so we're going to kind of simulate this by looking at this like CPT like mid-training, or sorry, like reasoning setting where we take this reasoning data set from this like OctoThinker paper, which is around like 70 billion tokens of like pretty high quality reasoning data. And we're going to like continually pre-train a bunch of models using this data. And we're going to limit ourselves to sort of a small slice of these full 70B tokens. So we're going to start with only like 4 billion tokens, and we're going to show you that like with these data efficiency tricks, you can train a good model only on 4 billion tokens to match a model trained on the full 73 billion tokens, which if you do the math is like a 17.5 data efficiency win. And so to like briefly summarize this table, this sort of first column corresponds to the base performance of the model we're starting with, which is like llama 3B. And then you can do sort of various interventions of continual pre-training at this 4 billion token scale, where you can sort of start with these like default hyperparameters people use. Then you can like lower your batch size, and you can like optimally tune epoching. And this like continually gives you more improvement. And then you can introduce these like ensembles that we did for pre-training, but now for CPT. And you'll see that like as you increase the ensemble member count, you also continually get better downstream benchmark performance. And our best ensembles, so both our 4 ensembles and our 8 ensembles, are better than sort of this baseline of standard continual pre-training on like the full 70 billion tokens, which is a pretty big data efficiency win. And it's also more compute efficient. So like the total flops we use to train these ensembles end up being less than the total flops you would use to train the 70 billion token baseline. So I mean, as infinite compute maximalists, we don't technically care about this, but maybe as a practitioner, this is a nice benefit to have as well. And so like these data efficiency wins do seem pretty real in like a variety of settings, which is nice. And so I'll sort of end the talk by like talking about some concluding points, like future directions we're excited about. And I think there were some additional questions that we can also get back to. So roughly like we've basically shown you a bunch of techniques that give you much better loss in this sort of finite data infinite compute regime. But like none of the techniques we're proposing here are really methodologically that new. Pretty much all of these are things people had tried in different settings. Like they're classic tricks that people did with MNIST and CFAR, or for like Pentree, Bank, or Baby LM. And like I think like the simplicity but like success of these methods in the data efficient setting sort of suggests that there is like a lot of free lunch for rethinking pretty much like every single basic like training decision that we sort of believe in like the current compute optimal like language model setting. And so there have already been like a lot of good works like starting to question these. So starting from things like architecture. So there's been this paper on looking at like energy-based models for pre-training, as well as a lot of work on like objectives. So things like diffusion versus autoregressive models, as well as like data augmentation, like these sort of synthetic data methods we've talked about, and like optimizer and like so on and so forth. And I think we sort of believe that we should be revisiting a lot of these assumptions we have for how we currently do training, because if these really simple classical ideas just work out of the box almost, like it sort of suggests there really is a lot of room for improvement. Another point we wanted to make is that like in this sort of modern era of pre-training and general remodeling, like we kind of believe that you can do much better in terms of data efficiency if you're willing to spend more compute. And like we're generally excited about like asymptotes as sort of an evaluation tool to tell you which algorithms like you should believe in. Like even if like asymptotes are something that only kick in at the infinite parameter limit, like we've shown various interventions that like push this frontier back. And I think we believe that having methods with clean scaling and asymptotes that you can estimate are methods that should do well in this like data efficient regime. So we're generally excited in that direction. And we also are excited to like try these types of ideas in sort of all of the other data efficient domains, like beyond pre-training. So things like personalization, like rare languages, like biology, robotics, so on and so forth. Like, I think we really hope that a lot of these ideas are more general than just language model pre-training, and can hopefully like sort of provide use in a lot of these other settings. It's also worth noting that like as sort of young optimistic academics, like this is like a fun direction to like do research in if you believe in scaling laws, because it lets you extrapolate performance at large scale with like super tiny experiments. And so I mean, even if you think 200 million tokens are small, like most of these experiments we did at the scale of 40 million parameter models pre-trained on 50 million tokens. And essentially all of the core experiments we found held up even as we scaled them up. And so in terms of like fast iteration, we had a good time with this paper. And so generally, like, I think we're excited about the structure. Yeah. I think that's sort of it for like the main concluding remarks. If there are any additional questions, we're super happy to take them. Okay. Yeah. So yeah, we can just start going through these.
Yeah,
Yeah.
sure. I guess there was one question a while back about weight decay. So I guess the question is like, why does the optimal weight decay jump to 30x and is it predictable? One thing that we found that was pretty interesting is that the optimal weight decay actually does have like a pretty simple relationship with how over-parameterized the model is. So basically like the parameter to token ratio kind of just does a very good prediction of what the correct weight decay is. So you can just use this to be able to predict it, that we don't have those clean scaling laws. Another question is there an efficient serving framework for ensemble models? So we do release an inference repository associated with this about like serving models, serving ensembles. So that might be nice to look at. But I think one interesting thing is like we think in the efficient serving for ensemble, you would never actually serve the ensemble, but you would just distill the ensemble. And one really nice way about the way we distill these ensembles is that if we train an 8 ensemble and we want to distill from it, we sample from each of the 8 models completely separately, generate 8 pools of data, and just mix those pools of data to train on at the end of the day. So one really nice thing is that we actually don't even have to inference an ensemble ever to get the data efficiency wins from an ensemble. So yeah.
Yeah, it's worth saying that we did go through the trouble of implementing efficient serving for ensembles, trying to distill in like sort of this joint way, and then realizing distilling the members independently actually gives us a better distilled model, which is like a really nice benefit.
Yeah, there's another question about have you tried ensembling in the infinite data limited compute setting? And do you think optimal ensemble member count given infinite data and finite compute will be larger than 1? My prediction for this is no. So I guess one thing that we can, one trade-off plot that's pretty nice to look at is if you look at the left plot over here where it's looking at validation loss, you can look at how the benefit of ensembling doesn't kick in until a sufficiently high parameter count. So maybe if your like limited compute budget is like very, very large, it makes sense. But I think in general, like if you have infinite data, you might just want to continue training on like training a single model for the correct amount of time. Yeah, these are all really good questions. Are there any more? We have, so I guess the question is about how if you change the ReLU bias, then you might actually be able to get further generalization. I think we have not tried this, so we don't know if the weight decay levels change or if the asymptotes move. I think it would be interesting to show this. I think this on top of other forms of regularization, we only studied one form of regularization because it was the minimal thing to get us to clean power law scaling. But I think it would be exciting to see use the asymptotes as a way to measure. So whether your regularization is helping your generalization in the sense that it's saving you compute, or in the sense where it's actually leading to genuinely better models. So I think the asymptote can actually distinguish between both of these worlds pretty nicely.
Okay, I have several questions to ask. So first off, regarding the regularization technique, so you are mainly tuning the weight decay. Have you ever tried like adding dropout back? Like this is like a very classical regularization technique.
Yeah, that's a good point. So I think a dropout is a very natural thing. It'll also have some interesting relationship with our ensembling experiments. We hadn't tried dropout because it was just getting a paid to tune all of these hyperparameters. But I think if you tune a dropout, I think it would probably bring the asymptote even further. And my understanding is that I would stack on top of ensembling as well. So I think it would be pretty interesting to see that.
Yeah, I see. And the second question is, how do you like the network in diffusion language model in the data constraint setting? You know, there are a lot of recent work like trying to show, okay, diffusion language model is like super data constraint and learner. How do you like this network?
Yeah, no, I think it's very good. And I think it would be really interesting to see how diffusion fits in within like the asymptotic framework to estimate like the infinite compute loss of diffusion and such, also relative to the language modeling stuff with the regularization and everything. I think it's very promising, and I think it seems like a real data efficiency improvement. Hopefully it stacks on top of the other games that we've discussed over here too. But I think like this, along with optimizer and like data augmentation and all of these things, hopefully they can all like stack on top of each other and give more improvements.
Yeah, I think maybe on a more meta point, we're like cautiously optimistic about like sort of different parts of the stack composing for data efficiency. Like we gave like a very preliminary example of this with like regularization and ensembling, but sort of there are a lot of these other things like diffusion as an objective, like architecture, like optimizer, etc. And these are things that like people generally study in isolation. And I think we're hopeful that like you can sort of do the data efficiency experiment in isolation and just like smush it together with everything else and like hopefully like see a better asymptote. Like we haven't really tried this like in depth with like these things like diffusion, but I think we're
Yeah,
hopeful.
I guess
Yeah.
parameter scaling and ensemble scaling show some good sign of life for that.
Yeah.
Yeah. Thank you for your answer. We have another question in the chat.
Yeah, sure. So there's a question about the potential of like universal looped or recurrent depth models. Yeah, I think we're like pretty excited about this. I think this is like another way in which you can train these implicitly larger models. I think the important part for these is that the main reason that larger models are helping is not some capacity constraint, but because it has better learning dynamics and better inductive bias and optimization. So the main question is, do these universal these depth models actually have the same properties? So it'd be interesting to empirically evaluate that and see if it's the case. But I think I can see a world in which it actually does have a big benefit. So I'm very curious to see.
Sorry to ask also a question.
Mhm.
What do you mean by, because you just said that you see larger models mostly benefit from a better training dynamics. So what do you mean by that versus,
Yeah, sure.
versus,
So I guess, yeah, that was a vague statement. Sorry. So I think mainly the common intuition for why larger models work better, one common intuition, not the only one, is that it's because the larger models have larger capacity and are more expressive and can express the more complicated functions that are important for the actual the task that you're learning for. I guess we believe the distillation experiments kind of push against this intuition that the larger models aren't helping because they're like larger and expressing more functions, but because they somehow generalize better in some learning dynamic sense. The distillation experiments are a concrete proof of this because they show these smaller models that even though they have the same capacity as a 300M model trained from scratch, distilling these 300M models does better. So it's not an expressivity concern, but it's about something more related to the generalization and the inductive bias of larger models.
I think it's also worth maybe clarifying here that like larger here is sort of implicitly relative to your like data size. And so like it might be the case that this is only something that happens like when you're over parameterized, because even our distilled models are still over parameterized relative to like 200 million tokens. So we don't know like if you can distill like the data efficiency gains into like, I don't know, like a 1 million parameter model or something like that. But like within this like regime, it seems like model capacity is not like sort of the determining factor.
Cool. There's a question about why we're using a shifted power law, so a power law with an asymptote rather than alternatives. So I think this was because we wanted to opt for simplicity. We wanted the simplest form that fit all our data because this is the type of thing that generalizes best and extrapolates most across scale. We found that this simple power law with an asymptote was enough to explain our data at like all of our parameter counts and data counts. So even though it's n equals 4 for a fixed data count, we do this across 4 data counts and see that the exponent is always 1. We see that the lines always fit the data points. So this kind of gives us some more confidence. The second axis in which we have confidence is that this is a theoretical prediction that if you tune regularization and you do all of your training correctly, you do expect a power law with rate exponent 1, like is something you can theoretically show. So this kind of gives us some belief that we're doing something not totally wrong. So this is kind of why we opt for the simplest form to do extrapolation rather than maybe like overfit the points too much. For what it's worth, we had also conducted a sensitivity analysis. So we reran all of these 4 points with different seeds and fit the line again. And we noticed that the law seemed relatively stable for the purple line. So.
Okay, so this is another question on Do you have any intuition on how full these distilled models are with respect to capacity? Are some models are just more amenable to further tuning? That's a really good question. I don't think we have like a super good sense of this. Like, roughly, I think to like exactly like quantify this, you need to build these data constrained distillation scaling laws. And there's been some really good prior work on this in like the compute optimal setting. I think from Apple is maybe the main paper to look at. But people don't really know how this changes when you're data constrained. And so roughly, like, I don't think we have a super good sense. I think like characterizing this would be really valuable in understanding like what this like loss frontier should truly look like in the limit of data efficiency. And so we're not sure, but it's like a very interesting like scientific question that we want to answer.
Yeah, and we do have some encouraging initial results where if you trade distill for longer, you can get even better performance.
Yeah.
So, yeah. Yeah, I think you raise a great point. So I think the reason that there's an interesting connection between the fact that normally pre-training, like the training models has double descent when unregularized under like the min-norm inductive bias. But what we're finding is that if you tune the regularization, then you get the correct performance. We don't have like a very like fine-grained explanation for this in terms of like the actual parameters of the model. But I guess we do find that it just really results in the power scaling. So perhaps we don't have a great answer for, and specifically in the language modeling sense, why it has like some mechanistic explanation. And another interesting thing is about this high weight decay. We find that the high weight decay is somewhat important considering that we're epoching, but it's extra important considering that we're over parameterized. So it might be something about the loss landscape for these over parameterized models rather than the repeated contexts.
Great. I guess if there are no other questions, we can end it here then.
Yeah. Thank you for your great presentation. Yeah.
Well,
Yeah.
thank you.
Yeah, thank you for all the great questions.
Yeah. this is
Can
quite
you
nice.
send the slides to me or to Kaiyu as well?
Yeah, sure. We can send it.
Okay. Thank you so much.
Yeah.
Have a good night. Bye.
Bye.
Bye.